In this last equation, it is a rough estimate of the failure stress. A rough estimate of the failure stress. Continuum assumption of English is not valid at the atomic level. Now this is a deep sentence. If you know solid mechanics well, if you know a little about advanced solid mechanics, there is a full course called continuum mechanics. So the idea is that matter is a continuum. There are no breaks. It is a continuous thing, and based on that everything is there. But if there are flaws and gaps and so on, then it is not a continuum. But you have to start the theory somewhere. So the standard theory, all very high level mechanics and physics, is based on the continuum assumption of matter. So English also assumed that, but it is not valid at the atomic level. Each atom is a different piece and so on. So the equation that you saw, the last equation on the last page, is a very good equation, because before that there was nothing. But now there is an equation to find the fracture stress or the critical stress based on elastic modulus and crack size and surface energy. Two other scientists, Galen and Kaninen, right? They derived a similar result, but they applied numerical simulation, finite element simulation, finite difference simulation, or something else, of a crack in a 2D lattice. Discrete atoms are connected by nonlinear springs. So it is not a continuum, it is consisting of discrete atoms, and the atoms are connected together, and when we do linearize the simulation for numerical, then each connection is like a non-linear spring. So we don't go into the details of that, but if you have done a finite element course, or if you are doing an applied finite element course, then that is the basis. That connection between material particles are spring loaded connections, and here we are non-linear. So by doing this finite element numerical analysis of finite difference, they found this equation: sigma f is equal to alpha E gamma s upon a raised to half. Alpha is a constant of the order of unity, means some multiple of 1 based on atomic force displacement law, and a is a. So if you will see that in the previous equation that English derived based on continuum theory, and this equation which was derived on numerical simulation, they are very close. They are the same in order. Of course, order means powers of 10. So they are the same, but this may be a small multiple of that and so on. Griffith energy balance, right? So how did Griffith did what we just said? It can be shown that, it can be proven that, it looks like. So Griffith started with the first law of thermodynamics. If a system goes from non-equilibrium to equilibrium state, there is a decrease in energy. We always told you that a stable or equilibrium means lowest energy. So there was non-equilibrium, things were moving around, and now it is in equilibrium, so a decrease in energy has happened. And Griffith did that in 1920. So he applied this idea of thermodynamics to crack formation. On the next page we will show you the same thing. There is a plate with a crack length of 2a, and it is subjected to a constant remote stress of sigma. Assume that the plate width is much larger than 2a, so that plane stress is a valid assumption. And we know that if a is much greater than b, then the earlier plate that we are showing you and this plate in this figure, they are the same. For crack to grow, sufficient potential energy is needed in the plate to overcome the surface energy of the material. Right? Surface energy of the material means that you have to apply at least this much of energy, or you have to do at least this much of work to create the fracture surface, isn't it? So you need some potential energy which is at least equal to the surface energy or more than that. So Griffith energy balance for an incremental increase in the crack area dA. So we take a very small infinitesimal crack area and an incremental increase, a small increase. So what are the conditions? E is the total energy, capital pi, this is capital pi, is the potential energy supplied by the internal strain energy and the external forces that we apply. Ws is the work required to create new surface S. And this equation you know from, right? Sigma F is 2E gamma S upon pi A under root. Right? So this energy balance is being applied. This energy balance is being applied. If we were doing this here, you will see that it is not a very complicated derivation and so on. But the way I am treating this course is that I want to have a breadth first approach, not a depth first approach. This means breadth, right? The breadth is large. So we cover many chapters. So we cover different parts of the course. But in any one chapter, we do not go too deep. So that is my approach, that in an introductory course, we do not go into the total depth of every derivation and so on, but we show you enough mathematics and mechanics so that you can understand more items in the course, right? So that is it. So this, as we showed you, that it is a very similar thing as earlier, but earlier you had an elliptical thing with 2A and 2B. This time we are just saying that this is a long sharp crack, long sharp crack. So if you say that 2A is much greater than 2B, then it is the same thing almost. And sharp crack does not mean that it is totally sharp. There is a small radius here. And the thickness of the plate is capital B, and the remote stress is sigma, right? So it is the same thing as we had before, but rather than an elliptical crack, we are saying that this is a flat sharp crack, or we can say that there is an ellipse where A is much larger than small b. Now we are again reminding us that there is a serious distinction between crack area and surface area, right? Because a crack means there are two surfaces. So the crack area is the projected area of the crack, projected area of the crack. So 2A is the crack length multiplied by B, 2A multiplied by B, B is the thickness, right? But the crack includes two matching surfaces, So the crack area is 2A. 1A is length of the crack into B, and the other A is also that. Griffith approach is also applicable to other crack shapes, right? Here, to make it very simple, remember that earlier we were taking an elliptical flaw, now we are taking a flat flaw, but we can do other shapes as well. So for example, fracture stress for penny shaped, you see they could have said circular, but remember the American penny or any coin is around, right? So penny shaped means circular. So embedded in a material, which embedded means not on the edge, inside. So we will show you the diagram on the next page, but we just do a little. E gamma S upon 2A is there, but 1 minus nu square has been added. Of course, A is the crack radius, and this nu is the Poisson's ratio of the material. Again, I am not showing you the derivation. So if you are a very die-hard mathematical oriented person, you will say, doctor, what are you doing? But generally you will be very happy and very thankful that we are not going into the complex derivations, and we are just taking the results. I mean, I'm trying to explain the physics and the mechanics of the material, but just giving you direct results. So this is it, right? This is the other thing, the same thing, but now this is a circle of radius A. Of course, because we are looking at an oblique view, so the circle is looking like an ellipse. Whenever we take, if we were exactly at 90 degrees to this view, this will be a total circle, but this is a circle of radius A. So this is called a penny shaped crack or a circular crack. So we have shown you the equation for an elliptical crack earlier, then a flat crack, and now a circular crack. With this background, now let us do a comparison of the energy approach with the critical stress criterion, right? Earlier, remember, in introduction chapter, we were talking of K1C, right? That what is the stress intensity of a critical level, right? So that was the stress intensity approach. Recently, in the last few pages, we were doing the energy approach. Griffith model is based on global energy balance of the whole plate and the whole material. For fracture to occur, energy stored in the structure must be sufficient to overcome the surface energy of the material. Fracture involves breaking of bonds. A stress on the atomic level must be equal to cohesive stress. This local stress intensification can be provided by flaws in the material. Similarity between the stress concentration and the energy balance equations is obvious, right? This is earlier equation, this is the current equation. E gamma s by 4a, 2e gamma s by pi a. So if you take out the numbers, they are of the same order of magnitude but different. And you see, E is there, gamma s is there, a is there, root is there, right? So predictions of global fracture stress from Griffith approach and the local stress criterion differ by less than 40%. So the two approaches are consistent with one another for the case of sharp crack in an ideally brittle solid, right? So this is, a big thing. Right now we are just showing you, but this is huge, that there are two totally different approaches. One is the stress intensity approach and the other is the energy balance approach, and their mathematics and mechanics and so on is different, but in the end the equations that you get have the same material constants, elastic modulus, surface energy, and the crack size, and the difference numerically is less than half and so on. The apparent contradiction when the crack tip radius is significantly greater than the atomic spacing. Right now we were saying that we are assuming a sharp crack, and we are assuming that it is not totally sharp. At the sharp V corner there is a small radius, and this radius is of the order of the interatomic distance x0. But if that is more, if there is more plasticity, right, when the crack tip radius is significantly greater than atomic spacing, so that will be more plastic, right? So Griffith model implies that fracture stress is insensitive to rho, because in the equation we do not have rho. English stress analysis, sigma f must vary with 1 upon root of rho. So these two are the problem, right? That in the English approach they are saying that critical stress is a function of radius of curvature, and in the Griffith approach it is saying that no, it is independent of that. So this is a major difference.